Hello guys, this is Saddam in Adobe and we will talk about center of mass, and now we will cover how many topics we have covered in center of mass and what are the topics that is left to cover in center of mass. So in center of mass, first of all, we have defined where it is. Okay, so it is like summation of all the smallest masses and their distances. So we have first defined what is the center of mass, and then we have also defined what is the velocity, and then we have defined what is the acceleration for center of mass. Okay, so and then we have also calculated how to calculate the center of mass for extended body, for an example like rod, continuous body, semicircle, okay, semicircular rod, or a disc. So these are the things we have calculated in center of mass for the body. Now we can also calculate for maybe hemisphere, maybe triangular seat. Okay, these are also a very good problem to calculate. This is called hemisphere. Where does the center of mass will lie? Now again, in third, we have to understand what is the implication of center of mass, which we will cover today. The implication of center of mass. Okay, then we will talk about conservation of linear momentum conservation, how that is arises in center of mass, and then we will more talk about what is the consequences of linear momentum. Okay, means if we have some linear momentum conservation idea, then we can do problem on collisions. Okay, so suppose if we have two objects, they are collide, then we will, because there are so many forces are there, how can we find out the outcome from the collision? Then we can find easily with the help of linear conservation momentum, and then we will see more in details how we can do this kind of things, and then we will talk about impulse. So this is the outline of center of mass. So if you guys haven't subscribed my channel yet, please do subscribe and hit the bell icon, and also please give me a favor, please share to your friends, and also give me some feedback in your comment box at how you're gonna like my videos, and because this is the most important, and I hope you will understand it. And yeah, let's understand. Okay, fine. As we have defined earlier that F is equal to F external is equal to dP over dt. Okay, we have seen this in Newtonian dynamics also, but we have also told you in my previous lecture that F external is equal to dP over dt, and now we have defined here P is equal to summation of this thing Vj. So J is equal to 1 to some n number of particles, and Vj we can write here d over dt. J is equal to 1 n mj rj. If you don't understand this step, please go back to my previous video and you will find out what is the meaning of it. So what is the meaning here? So F external is equal to nothing but, I can write here d over dt. Again we will, d over dt has come from here, d over dt is from here, and then j is equal to 1 up to n, and hence mj rj. Okay, now what we can do here, we know because of this thing, if RCM, R is your center of mass, then we have defined here 1 over m, and here it is mj rj. Okay, now we are seeing here mj rj. Okay, replace this guy from this thing, this equation. So if I'm going to replace this, it will be nothing but d2 over dt square, and then I'm going to replace here that it is RCM over m. Okay, now as you can understand, sorry, RCM into m. As you can understand, m is your constant. What we can do here, m d2 over rcm or dt square, which is nothing but F into ACM. So if you apply some external force on any object, as we have treated earlier when you were trying to solve Newtonian equation for pulley, maybe some wedge motion, maybe if we will see in case of sun and earth, the force acting on this extended body is as if कि जब आप फोर्स लगाते हो किसी एक बॉडी पे तो आप क्या कर रहे हो, बॉडी के हर एक पार्टिकल पे नहीं लगा रहे हो, एज इफ कि आप कोई उसके सेंटर ऑफ मास पे लगा रहे हो, यानी कि जब आप उस पर फोर्स लगा रहे हो तो होल बॉडी के बजाय क्या कर रहा है, वो एक उसका सेंटर ऑफ मास क्या कर रहा है, मूव कर रहा है. ओके, तो मैंने कहा था कि ये जो बॉडी है वो क्या कलेक्शन ऑफ ऑल द स्मॉलेस्ट पार्टिकल बना है. जब आप फोर्स लगाते हो तो सब पे एक साथ फोर्स लगता है, तो आप इन सबको हटा के क्या कर सकते हो, पॉइंट पार्टिकल मान सकते हो, जिसे हम दिखाते हैं दिस गाइस से. सो एज इफ दिस डायनेमिक्स ऑफ मोशन, कि इस सेंटर ऑफ मास का अगर आपको डायनेमिक्स पता है, ट्रेजेक्ट्री पता है, तो वो क्या होगा, इस होल बॉडी का ट्रेजेक्ट्री होगा. सो दैट इज द टू मोस्ट इंपॉर्टेंट. सो दिस रिजल्ट सेज मी दैट या फॉर एनी एक्सटेंडेड ऑब्जेक्ट वी कैन ऑलवेज make it as if it's a point particle, and if we know everything about point particle, then we will know what is the trajectory of this whole body. So that is the idea. Well, F external is equal to m ACM. It's a very important result, and note it down please. Another thing is that, as we have seen, let's find a definition of momentum. Now we have already seen it, mj rj. So what we can do here, again replace by m rcm. Okay, so it's again same as if why mcm, it's again as if your center of mass is moving. That's all. So in some sense, in some way, what is the kinetic energy of any object? So kinetic energy will be nothing but p square over 2m. Okay, so I can define here p square, so therefore it will be nothing but m square v square cm over 2m, which is nothing but half m vcm. That's all. So these results are very amazing results in itself, because this gives us the power to unlock many features. What is the meaning of how we can unlock it? So for example, if we have seen the projectile motion, isn't it? Projectile motion, and we have treated this projectile as if it's a point particle. Okay, but in many cases we are playing cricket or we are throwing something. What we have some object. Okay, the object is a collection of whole particles, but as we have projected it, what is actually happens? Maybe it is spinning. Okay, so you just took a ball, spin it and give it there. What happens is that this ball is actually projecting in this way, so you don't have to care about each and every particle of this object or the large component of this object. You just track its center of mass. You just track its center of mass, and whatever the ball is doing, whatever the center of mass is doing, it will simply gives you everything about this ball. For an example, your ball is here on the way here, and somehow it explodes. So what happens is that another part, अगर ये एक्सप्लोड होता है, ये बॉल एक्सप्लोड होके दो छोटे छोटे बॉल्स में चेंज हो जाता है. ओके, somehow internally there is no any external thing which is tear apart, but internally क्या होता है, ये एक्सप्लोड होता है. एक्सप्लोड होने के बाद क्या होगा, कुछ पोर्शन क्या होगा, इसका इस तरफ गिरेगा और कुछ पोर्शन में भी इसका इस तरफ गिरेगा. बट एक चीज हमेशा याद रखना, the thing is that its center of mass will always follow only this trajectory also. इसकी जो parent trajectory है, ये center of mass की है. Maybe this particle is 1, this particle is 2, So maybe this particle is too much heavy, so it lands there, and it's light, this lands there. Okay, but you have to follow the trajectory of this particle. Okay, the center of mass. If you know the center of mass, if you know the trajectory of center of mass, you know the range, the time period, then you can calculate where this one has landed and where the 2 has landed. Okay, now you can say that why we can track, because we have already told you that the motion, we can always assume this particle as a center of mass. Now center of mass means what? For any object, maybe this object, the center of mass lies here. What happens is that it distributed everything uniformly. This point gives you an idea that if you can balance the whole mass distribution from the single point. So either it may get explode, okay, it has got explode, but the thing is that it won't lose. Center of mass lie here, 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 this way. If the bomb explodes, if something explodes by itself without interfering any external forces, then you can easily say that yeah, this thing happens. Not a big deal. Okay, very good. Now another thing is that, for example, you have a center of mass, we have here, which is nothing but dp over dt, which is nothing but macm. What happens that if you have an object, और मैंने क्या किया कि टोटल अप्लाइड फोर्स और इज 0, ओके, यहाँ पे कोई फोर्स लग रहा है, इसमें इस तरह के जब टोटल अप्लाइड फोर्स ऑन एनी ऑब्जेक्ट गिव्स यू 0, all the applied forces, which is called external force, is 0, then we can say that the momentum is always conserved. 0 means momentum is constant or conserved. If this momentum is conserved, what does it mean? It means that mjrj, or in some sense mrcm, is not, it's not mjrj, it's r dot. mrcm is constant. So if mrcm is constant, we can always define the velocity here. So velocity we have already defined here. Velocity is 1 over m, m1 v1 plus m2 v2 plus m3 v3 and so on. Okay, now for acceleration we have defined it here, m1 a1 plus m2 a2 and so on. This was for acceleration, this was for velocity. So if we have all the applied force on the system is 0, then we have also here the momentum is conserved. Okay, so momentum is conserved means that p initial is equal to p final. For an example, you got system, okay, there is no any external force, or all the external force applied on this thing is completely 0, and maybe it explodes. After something it explodes in two objects. What happens is that here whatever the initial momentum is, it will equal to its final momentum, and that's the pretty much amazing thing here. Okay, now you can see here this is m1 v1 and this is m2 v2, because from this guy, what does it tell you? It tells you that, for an example, we have this ball and after that it explodes. Now if it explodes, okay, it was in rest, it will explode. Okay, what will happen to this? So according to linear conservation of momentum, or we can say that as we have understood right now that there is no any force, the total force acting on it is 0, then therefore we have momentum is conserved. Well, as if it's upload, then again because of this, if it is in rest, so it will maintain it in some way in rest. So if it's going this way, it will go in that way. So I am here somewhere because my center of mass is somewhere this one, so I will again, my coordinate will be in this way. Okay, my coordinate is in some center of mass we have seen. So here from this coordinate, from this center of mass, our situation was in rest. So from here the situation also must same, because why? Because there is no any external force applying here. So P initial is equal to P of final. Okay, now we have two masses M1 and M2. Got it? P initial of this object is was 0, and then P final. What happens to P final? So maybe it has velocity v1, it has velocity v2. So m1 v1 plus m2 v2. So I want to understand what is your v1. So it will tell me that v1 is equal to minus m2 over m1, simply v2. So if v2 is my positive, means that the velocity is in positive direction, then obviously this v1 is in negative direction, which again tells me that this and this will be negative in some sense, and then your initial momentum is equal to the final momentum. This is very interesting in terms of center of mass coordinate, because this comes from the simple thing, P is equal to mj rj dot, because we have assumed that all the this ball or this object has made with tiny particles, and maybe it explodes without having interference of any external forces, or maybe whatever the force is acting on it is completely zero. Okay, so we can apply P initial is equal to P moment P final, and we have chosen our coordinate in such a way that it's again in center of mass. From here we had the situation in rest, so obviously from there it has to be in rest. So if it is in rest or it's in rest, then we can assume that yeah, it is 0 and this one. So if I am choosing my coordinate wisely, then our calculation is getting really gets boiled down to very simple solutions. Okay, so if you are choosing any different coordinate system, okay, maybe you are choosing some different coordinate system like here and there, then you will get the same answer. Okay, the answer won't change, but the thing is that your calculation becomes too much horrible. You can get from this one step and you maybe have to calculate the several steps. So we have to choose the coordinate system very wisely. That's our way to do calculations in physics. So this was the very interesting thing, and this explosion, that it simply explodes by itself. Okay, this happens in nuclear phenomena, because you know you got an atom and there is a nucleus, and what happens from nucleus, there some alpha particle gets ejected out. So if you got some nucleus like ball, and after some time there is alpha particle and the rest of the recoil, we say. And if I know the velocity of alpha particle, then find the recoil velocity. Okay, so this is the way, because this alpha particle ejecting from this nucleus, it's completely not due to any external force, it has got to do with some internal force. So I always say that we don't have to worry about these internal forces, therefore we can easily apply this phenomena that P initial is equal to P final, and we get all the results down here. So this is a very beautiful example, and not example, it's a very beautiful concept, and it's a great implication. So yeah, that's all in the center of mass, and we got some idea about linear momentum conservation, and we will try to understand the collision cases in more detail, that how can we solve the collision cases. For example, there is a ball and there is a ball, maybe two objects in a frictionless table. Okay, there is no any external forces. Okay, the gravity is acting towards it, but you know gravity is for this one, but we want to analyze the velocity this way, so there is no any acceleration there. So if my acceleration is 0, therefore P is conserved in x direction. Okay, so you got to understand it. So if my P is conserved, then we can easily find out what happens if it collides with this guy, what is the final velocity, and so on. Okay, if it has some initial velocity, what happens to its final velocity, and we can also calculate some different things. Again, in a projectile motion, what happens is that there is a guy here, So can you apply this? Can you apply the conservation of momentum in projectile motion? But yes, it was in G field, which was down here. But we have already told you that in x direction there is no any acceleration in x direction. So if I know this point, maybe this point A and this point B, so I can write here P initial is equal to P final. So I know if this was an M, and so U is your vector quantity. Now P final. So U quantity is nothing but this x, because you know we can always conserve momentum in the x direction because acceleration in x direction is 0. Therefore dp over dt is equal to 0, which was in x direction. We cannot apply this in y directions. So if p initial is equal to p final, what is the velocity here? So this one is maybe v. I don't know what is the velocity here, which is always in x direction. Therefore m is cancelled out. Now u is there, theta is here, so it was u cos theta. So this was u cos theta is equal to vx. Therefore the surviving velocity at this point is u cos theta. As we have already seen that when this projectile got there is no any y component, there was all only u component, u cos theta. Okay, the velocity in x direction. So we got this value u cos theta. So that is too much easy to understand if you know what is the conservation of momentum and where to conserve. Where there is no any force, there is no acceleration, we can always conserve this momentum. And if you understand how to conserve this momentum, then there are so many problems which will get solved easily without any too much effort. So I hope we will discuss the collision cases in more detail in later video. Thank you so much. This is Saddam, AutoCAD, signing out.